So today we are going to start Dijkstra algorithm. So Dijkstra algorithm finds the shortest paths between nodes in a graph. Okay, so the main thing that Dijkstra algorithm does is it finds the shortest path between nodes in a graph. Okay, so when we talk about finding the shortest path, and that too single source shortest path, so this is an algorithm which finds single source shortest path. Okay, so single source shortest path problem can be tackled by three ways. Okay, so it can be tackled by three ways. First is single destination shortest path. Second point is single pair shortest path. Third point is all pairs shortest path. Okay, so Dijkstra algorithm solves the single source shortest path problem on a weighted directed graph. Okay, so the graph must be weighted directed graph, okay, or digraph. G V comma V is the vertex and E is the edge, where all edges weights are non-negative. Okay, so non-negative means we can write W U comma V greater than or equal to 0. Okay. For all edge U comma V belongs to E, capital E. Okay, okay, so this Dijkstra algorithm, we can look at it from three aspects. One is the insertion, another one is the decrease key, another one is the extract mean. Okay, so you can also call Dijkstra algorithm as a combination of DFS and Prim's algorithm. So it resembles depth first search plus Prim's algorithm. Okay, so Prim's algorithm is used for finding minimum spanning tree, right? So DFS plus Prim's algorithm for computing minimum spanning tree. Okay, so it resembles Dijkstra algorithm resembles these two algorithms. Now Dijkstra algorithm also, so Dijkstra algorithm is implemented by, it can be implemented by mainly by priority queue. Also sometimes we use mean heap algorithm. So how you are going to choose the the minimum cost path from u to v. That is the catch, and that can be explored using relaxation concept. Okay, relaxation. Now what is relaxation? If length of the new path from S to V is shorter than dv, then update dv to the length of the of this new path. Okay, so situation is something like that. Consider an edge from a vertex u to v. This edge you are considering u to v. Suppose we already processed u so that we know du equal to delta s comma u. Okay, so we are here du, and here is our starting vertex s, right? And then there are many vertices in between, and there may be other paths also available from this side to this side. This is all directed graph, so arrows will be there. So suppose we already processed u so that we know du equal to delta s comma u, and computed a current estimate for dv. Okay, so this is estimate, this is the estimate, this is the cost from s to u, and this is also a cost from s to v. Okay, current estimate, you can call it current estimate. Okay, and we know du equal to delta s comma u, so du equal to delta s comma u. So this is we know that this distance is this much du. Okay, and we computed a current estimate for dv for vertex v. Similarly, we have computed this dv also. Okay, so we can write that dv equal to delta s comma v. Okay, then there is a shortest path from s to u with length du. So if this is done, this is true, then we can write that there is a shortest path between s to u. Okay, and there is a path from s to v with length dv. Combining this path from s to u with the edge uv, we obtain another path from s to v with length du plus w u comma v. Okay, so another path we have established from s to v. Okay, and that s to v is with length du plus w uv. So dv we have calculated, and then so what I am trying to say, du plus w u comma v is that the currently we are in this situation. Okay, if, and also we have calculated estimated path from s to v. S to v have calculated. Okay, this is estimate from traversing from s to v. Okay, if du plus w u v less than dv, so this newly estimated path cost from du to dv, that we have actually recently found out. Okay, thinking that this will bring the lesser cost of visiting u to v than this one. So this one is the earlier one, we have calculated dv. If this is a situation, if this is less than dv, that new path that we have actually explored, then we replace the old path that is s to let us say x and then V. This is, let us say, X that we earlier explored. This path, we will be replacing this path with the new shorter path, with the new shorter path S U comma V. Okay, hence we update, hence can write it over here. Hence we update dv equal to du plus w u comma v. Okay, and the predecessor of v is nothing but u. So if you write the relax algorithm, pseudocode you can call it, it will be like, now let us take one example and solve the problem. So this is the example we have taken, one example to solve the Dijkstra algorithm. So you can see that, so we have to use this repeat relaxation concept. Okay, repeat relaxation concept you have to use. So you can see in step number 0, we have V, and then we have dV, and these are the vertex S, A, B, C, D, and then we have predecessor of V, and then we have color. Okay, we'll color the vertex, color of V. Okay, so initially the source vertex cost is 0, and then we have infinity. So all the vertices initially, the distance, we assume that it is an infinity. All the vertices are at infinite distance, so we will put all vertices as infinity. Okay, and then predecessor of S is nil, and then these all are nil. Okay, N stands for nil, and initially all the vertices are, let us say, white or white. Okay, that means not colored. This is step number 0. So at step number 0, what will happen? We have to first we will replace. So our initial vertex is which one? So our initial vertex. So, and also we have to maintain a priority queue. Priority queue, where we will be having this V. And we said, as we said, that Dijkstra algorithm can be implemented either by priority queue or by mean heap, and we will discuss the time complexity later on. This is dV. So initially it is 0, and another infinity. Okay, so what are the adjacent vertices of S is nothing but A and B. Okay, A and B. So you have to work upon A and B. Okay, so if we work upon A and B, so in step number 1, step 0 is over. Step number 1 are, so these are the vertices adjacencies to A and B. So this vertex will automatically become, let us circle it, black. Okay, this vertex will become black. That means we have visited this vertex. Okay, so this vertex S will become black. Now in step number 1, again we have to write this V, and then dV, and then predecessor of V and color. Okay, so we have this S, A, B, C, D. Here we can see that this so this is 0 initially, source vertex, and the cost of visiting A is nothing but 2, and the cost of visiting B is nothing but 7, right? And C and D is again out of reach, so this will be infinity, and predecessor of S is nil. Predecessor of S, A will be S, B will be also S, and this also will be nil and nil. Okay, so color, which one will be colored next? Only this one, this vertex X will be colored. So you already have colored it, black color. Okay, and then others will be still white. Okay, now what will be the priority queue? Priority queue will be, priority queue at this situation will be V, S, A, B, C, D. So this is dV. So this priority queue will be, this one will be black, S will be black, and all other will be white. And we have already made black visited vertex S as black. Okay, so this is step number 1. Now in step number 2, what will happen? Let me rub this thing. Adjacent vertex of now it is nothing but minimum of A and B. Okay, minimum of A and B, and minimum of A and B is nothing but A only. So we can A, because out of this A and B, A has the minimum cost, which is nothing but 2 path cost. So A, now adjacents of A will be B and B, C, D, all 3 vertices. Okay, this part is the upper part. Okay, this is not we are discussing. So even you can C, D, adjacents of A, B, because out of A and B, A has the minimum cost. We can reach A by a minimum cost. So, and also because we have visited, we have checked this A and B, this infinity will be striked out, and it will be relaxed by 7, and this infinity also will be striked out, and it will be relaxed by 2. Okay, so now we are at position A. So adjacent vertex is B, C, D. Adjacency vertices of A is nothing but B, C, and D. Okay, B, C, D. Now what is dV? dV is nothing but the distance is, this is 0, and A is now 2. Okay, B is now 5. B is 5. Once we visited A, then the vertex of 7, which we have initially relaxed with 7, now it can be visited by 2 plus 3, 5. So further you can strike this, and you can write 5 over here. So B is nothing but 5, and C will be 10. C will be 10 because we can visit C by 8 plus 2, SAC. So 8 plus 2 is nothing but 10, and D will be nothing but 5 plus 2, 7. Okay, so these are the new dVs we have, and the previous predecessor of S is nothing but nil, and then predecessor of A is nothing but S, and all this BCD we have predecessor as A, right? And color will be what? So this S, B, A we are visiting, so this S already we have made black, and now we are going to make this is 2. Okay, now we are going to make B also as black, and then we have these 3 vertices are white. So B now, and priority queue also will be changed accordingly. S is already black. Now we are making B also as a black. Okay, black means this is out of this queue. Okay, priority queue. That means we have printed these two vertices S and A. Okay, S and then A, visited vertices, printed vertices, rather you can write printed vertices. Okay, S and A. Next let us see. So BCD, among this BCD, whichever, and then these remaining vertices will be white. Okay, or in fact we can remove this from priority queue. We can write a new priority queue, because in priority queue we are actually dequeuing it, right? So V, DV, and now the remaining vertices are nothing but BCD, and BCD, remaining vertices BCD. And what will be the cost of that? BCD is nothing but, once you visit A, then BCD we can, the vertex of B will be updated by 5, C will be updated by 10, and this is 7. Whatever you have written over here, same thing. Okay, and remaining two vertices we have deleted from the queue because it's a priority queue and we have printed it. Next, at step number 3, let us say, so in this case, among BCD, whichever is the minimum cost, B has the minimum with minimum path cost B we can visit. Okay, and now by this time we also make this vertex A as a black vertex. Okay, we can make it black. So that we have already done over here. So these two vertices. Okay, now the nearest vertex and the adjacent vertex to A, which has a minimum cost, is nothing but B. So we will be choosing B. So this adjacent vertex of A will be changed over here. So let us rub it. So here, so now we have adjacent vertex of B, which is nothing but C, A and C, right? A and C, because again we have this arrow is also there, so A and C, and A already we have visited, so we have to look at C. So similarly this thing also will be changed. So now after this step number 3, so this is step number 3, this also will be 3, let us say this is 3. So in step number 3, how this matrix will change. Now this will be A, 2, 5, 6. So now once you visit B, then you see here, because the updated value of this is 5, visiting B from S to B is nothing but 5. So 5 plus 1, 6. B to C you can visit it, cost 6, and if you come to this S, 2 plus 8, 10, which is more than 2 plus 3, 5, 5 plus 1, 6, again 6. So we have to just we have to change this. So C, we have to update this value of C with 6. We will update it. We will update this one with 6. So this is 6. Once you update this 6, visiting D also will be changed. Visiting D will be already 7, so there is no need of changing C because there is no update. Update is not possible for D. D will still be 7. Now B, for B the predecessor is A. For C, predecessor will become now B, not A. So this will be omitted. So it will be nothing but this will be changed, right? And so this will be nothing but, for C the predecessor will become B now, right? And 7 will be as it is. And now already we have made, now we have to make B also as black. Okay, black, we have to dark it. So here so this vertex will become black vertex. Okay, so we have to make the color of this vertex B as again this black. Okay, and C and D will still be white. Okay, C and D will be white, and accordingly this priority queue, our priority queue also will be changed. So this is our priority queue for step 3. Okay, so in this case this B we will remove this B, okay, from the priority, we will dequeue this. So only we have C and D, and C, this thing will be also changed. It will be C can be visited by 6 and D can be visited by 7. Okay, C also value has to be updated, so the value of visiting C and will be updated. So this thing will be, initially it is 10, I guess. After 10 it is now can be reached by 6. Okay, and D can be visited by 7, because D initially also we should have changed it by 7, because we can visit S, A and D 5 plus 2 7. So this is there 6 and 7. This is my new priority queue. Now what will happen at step number 4? So okay, now step number 4, what is going to happen? So our next vertex out of this C and A, obviously A already has been visited, so we'll visit C. So C adjacent vertex is nothing but D, because already we have visited B, so D is the adjacent vertex, which is step number 4. Okay, now here also it will change 5 6 7. Nothing is going to change much, so only thing is that nothing is going to change. Color to the node C has to be changed now. So this B has become black again, already black, and now this C also will become black. Okay, now this C will be changed here, it will be black only, so we can write it to B. Okay, and let us make it black. So S A B visited what is S, printed what is S A B, and then C. Okay, now this is nothing. Okay, so this is done, and then finally we have this vertex called vertex D, which can be visited directly from C, and then finally it will also be black. Okay, so this is the final vertex will be D. Okay, so from Q also this C will be deleted from the Q, and this will be also black. Okay, and then finally at step number 5, okay, step number 5, what will happen? This only D will be there, so D will be displayed. So this is how this so finally D will be displayed. So this is how this priority queue and this Dijkstra algorithm works using repeat relaxation. Okay, so I think we have completed this. Few interesting point that you should know about Dijkstra algorithm is that Dijkstra algorithm is the combination of DFS and Prim's minimum span tree algorithm. Okay, and finally the priority queue, when everything will be displayed, all the vertices, the priority queue will be nothing but phi is nothing but empty. Okay, empty. So time taken by the Dijkstra algorithm is nothing but O V square plus E. Okay, O V square plus E, and so you can write it big O of V square. So this is when we implement priority queue. Okay, it is believed that it can be reduced further if you use mean heap concept. Okay, so time complexity and other aspects we can discuss in other days. Okay, other time. So thank you very much for watching this video.